Okay, so then we have seen examples of dissipation and dispersion error. In the example I showed you at the end, for the dispersion error, the initial condition was on the left. The pulse was on the left. It should have been propagated correctly to the right, but you saw the waves with the small wave numbers were correctly transported. You could guess it, but the waves with the high wave numbers were not. So they are lagging behind. So that is the typical of the dispersion error. Now, we want to leave the upwind method and to briefly look at two other methods that are also possible to use for to solve the linear advection equation. And the first of these methods is the Lax-Friedrichs method. And so Friedrichs is the same name as in the CFL, that's the F in the CFL, the Courant-Friedrichs-Levy. And Peter Lax, he has been an important, prominent mathematician who got the Abel Prize a few years ago, which is a kind of Nobel Prize given here in Norway. So, and there, the approximation of the convective flux at J plus 1/2 is done in a similar way as for the upwind method, which we wrote in this special form, where we have the average of the convective fluxes evaluated with the values in the cell J and in the cell J plus 1 for the phase J plus 1/2. But then our coefficient is not the absolute value of the velocity, but instead delta x divided by delta t. And then we have here the difference, tj plus 1 and tj. So that is the big difference here, this here, to the upwind method. In this method, I say only very little about it. It's really a robust method. So when you have a problem that is really tough, you can try this one. But you must always be aware of that this method is very dissipative. And you can also see when it is very dissipative, because in the analysis of the flux we did for the upwind method, we can also do that here. If we divide by delta x and multiply by delta x, we see that the numerical viscosity, I write it in this form, that is then delta x squared divided by 2 delta t. So we have the 2 here, we have the delta x over delta t here. When we divide by delta x, then we see here the approximation of the dt dx, and this is then the numerical viscosity. And you see the problem. The problem occurs when you let delta t go to 0. Then you get a really large numerical viscosity, and that smears all what you have. So the whole physics is gone. So you should be careful with that when delta t goes to 0. So then another method, also going back to Peter Lax, but I think with his former PhD student Wendroff. That's the Lax-Wendroff method. And it has a similar starting point as the one that we have been, as the Lax-Wendroff, as the Lax-Friedrichs method, but instead it uses the following. So that is then the 20. We say then that the convective flux at J plus 1/2 is equal to, we start again in a similar way with the arithmetic average of ut at J and ut at J plus 1. And then we have here the following term. We have the u squared delta t divided by delta x times the difference in tj plus 1 and tj. So here the coefficient that we have in front of the term that is responsible for the numerical dissipation is different. So for this, in this case, the numerical viscosity is then if we have already the delta x here, so that is nice. So we see it as u squared delta t, u squared delta t half. So that does not have a problem. Instead, the numerical dissipation goes to 0 as delta t goes to 0. So that is better. So that does not suffer from this problem that the Lax-Friedrichs method has. And it has another big advantage, that it is second order delta t squared and delta x squared. When we use for the time discretization, remember here this is only the flux discretization, that is the space discretization that we discussed, when we use the explicit Euler method. So that is a nice feature, that we get second order both in time and space. However, it is not useful for applying it to discontinuities, because there we get oscillations. So there we have to do something different. But if we have a smooth solution, then this method is good. So we could say much more about that, but we'll stop here to move on to a new chapter. So we have now the linear advection equation, the finite volume method for the linear advection equation, where we have done very much analysis on the upward method. That is with good reason, because it is so important. Now draw our attention to the finite volume method for scalar conservation laws. So far we have just been dealing with linear problems. Both the heat equation and also the linear advection equation are linear problems, but we shall now attack nonlinear problems. Have you copied that? That is then chapter 5. There we are. The heading, finite volume method for 1D scalar conservation laws. That. First we look at the equations and try to understand what they contain. And it's always good to have as much mathematical understanding as possible of the equations that we want to solve. And we shall see it is also useful for devising the numerical methods and also the boundary conditions. So the finite volume method for one-dimensional scalar conservation laws. So we shall consider hyperbolic scalar 1D conservation laws. And that those that we are going to consider are of the following kind. We have an integral. And now again our problem is now x, and we have now we change to a general conserved variable, we call it u. Could be velocity, could be concentration, could also be temperature. It can be any conserved variable. And we imagine that we are looking at an interval that is bounded by the faces xw for west and xe for x east. And we have there some solution, and we want to look what is happening there. And when we derive a conservation law, we do it for the integral form. So then we will have then here the integral from xw to xe. So the integral from the western to the eastern phase, where we integrate over the time derivative of our conserved variable. And then in general, we will have a nonlinear flux, which is then, we call it f of u, and that will be evaluated at the eastern phase at a certain time t. And here, if we would like to specify, that is a function of x and t. The u here is a function of x and t. So then we have the flux that is leaving the eastern phase minus the flux that is entering the western phase. So, and that is then when we just consider the simple case, that is just 0. So we do not consider source terms at this point. And in here, in this equation 1, we have u as a function of the space, that is the x-coordinate, and time t, that is our conserved variable. And the f of u that is appearing there, f of u, that is the flux function. And that is, in our case, that makes it interesting, usually non-linear. It can be linear, but if it's linear, then we fall back to the linear direction equation. Usually non-linear. So, now we argue if this flux function f of u is smooth, we can derive it, and if the derivative is continuous, so then we call that here smooth. So if f of u, and u in turn is a function of x and t, if that is smooth, then we can express the integral form also in differential conservative form. So that is the integral form 1 can be expressed in differential. And the form that we write now is called conservative, because we can write it, the flux is appearing as just a derivative. Conservative form, and that is the following. We have then the time derivative of u with respect to t plus, and what we use here is the fundamental theorem of calculus, that we can express this here also as the integral of the space derivative of f of u over the same interval. This must be true for any interval, so then the time derivative plus the space derivative of f of u must be 0. So that leads then to this differential conservative form. So there is now here this, I introduce now this expression here, conservative form. Or we can express it also, another possibility, non-conservative form. Which is also called quasi-linear form. And that is the following. There is 3. So here the conservative form we have really a clear space derivative of the flux, and this is what we understand as conservative. It's coming directly from the integral form. But when we do a step further, the step further would be here to apply the chain rule, because here we have f is depending on u and u is depending on x and t. But here we have only to consider the derivative with respect to x. So then we apply the chain rule, and we get then the du dt plus the f prime of u, and that I call a of u. Here I introduce that shortly, and then we have the du dx is equal to 0. Where that is important to note here that where this a of u is the f prime of u, or right in this form f of u du. And that has a name, that is the characteristic speed. Is the characteristic speed. So this is the f prime of u. That is the chain rule. The f du times du dx. And this a of u is this. So that tells us then that we have also here a propagation problem, but the propagation velocity a of u is not constant in general. We have a nonlinear problem, then this propagation speed, that is the characteristic speed, depends on the solution. So, the prominent example of such a 1D scalar conservation law is the implicit Burgers equation. So, the prominent example of such a scalar 1D conservation law is the implicit Burgers equation. That is after the Dutch scientist Burgers. There's now also a Burgers Center in the Netherlands, where they also deal with fluid mechanics. And it looks like this. It is du dt, the time derivative of our conserved variable, and the flux function is now u squared half. So that is our f of u. Is equal to 0. So that is the implicit Burgers equation. And that is modeling the 1D implicit momentum equation, actually for incompressible flow, but without pressure gradient. Modeling the 1D implicit momentum equation without pressure gradient. So here we see the nonlinear flux function is u squared half. So that is clearly nonlinear. And this equation has features that we also shall see later on for the one-dimensional Euler equations of gas dynamics. So we shall see that we can describe a shock with that, sharp discontinuity. We can describe an expansion plan where things are changing smoothly, and that makes it interesting. So then we can note that the nonlinear flux that we have here, or the nonlinear flux function, in this case is, for the nonlinear, for the implicit Burgers equation, is f of u is u squared half. So the characteristic speed that is what we defined before, that is the a of u. You see that is the f prime of u, and that is the derivative of f of u with respect to u. So that is 2u divided by 2, that is simply u itself. And the flux function is convex, so f of u squared half is convex, and the definition of that is that the second derivative of f with respect to u, you see we have already taken the first derivative, the second derivative then is 1. What we need to be convex is larger than 0. So that is the definition of a flux function being convex. So that we have here. Good. So then we try to understand a little bit more about this equation and its solution. So let's assume that we have an initial condition. For the initial condition, acronym IC. 6, we assume that we have u given at the time t equals 0 as a given function u0 of x. Let's assume that it is given everywhere, or that we have a periodic function that we extend to the whole real space. Then the exact solution of the implicit Burgers equation can be implicitly given by the following. For this initial condition, the exact solution of the implicit Burgers equation is 4 is implicitly given by following, that is 7, that we can say the solution at any time t for at x is equal to the initial condition u0 of x minus ut. There you see it is, we cannot determine it directly because the unknown that is appearing tells us also at which place we have to look. So therefore we cannot directly say what it looks like. But when we put this in the equation and we do the derivation in the similar way as we did for the linear advection equation, we'll see that this is okay. But let us try to understand now what are the characteristics for this equation. We have seen the characteristics for the linear advection equation. What are the characteristics for the implicit Burgers equation? So the characteristics are the following. So they are the curves x as function of t with the slope dx of t dt is equal to u, the characteristic speed, which is u for the inviscid Burgers equation. So then, if we assume that u is satisfying the inviscid Burgers equation, then we can check what happens on such a characteristic for the solution. So we look on the characteristic, that is now x is not independent, is dependent. It has then is defined by this slope. And we look at the time derivative. Then we do the same as we did for the linear advection equation. We apply the chain rule. We do the derivative with respect to t, this first. And then we do the derivative with respect to x. But this is dependent on t, so we have to add a dx of t dt term. And this here is according to our choice, is just above, that is equal to u. So that is then equal to u. So we get then that is the u dt plus u du dx. And we had assumed that u is the exact solution of the Burgers equation, so this is 0. So that means then that u does not change when we are on a characteristic. That means u is constant on a characteristic. So that is the consequence, that u is constant on characteristics. And actually then this is determined by the initial condition. Determined by the initial condition that was 6. So it turns out that this is then the slope then is determined then dx of t dt, that is the slope of the characteristics, is determined then by the initial condition u0 at the foot point of the characteristic which is then x0. And if we start from there, the solution is constant, then also the slope of the characteristic is constant, and we get straight lines for the characteristics. So then, from that we can conclude that the characteristics are straight lines with slope slopes u0 of x0. Because x0 varies, then also the u0 of x0 will vary. Okay, let's see. What does that mean? Let's look at an example. We have x and u in this plot, and we plot also in another plot, we plot x and t. So we assume that, say that the initial condition, that the origin would be there in this point. So also then would be, say, the origin here would be there. And we assume that we have, say, maybe a sine wave in the beginning. So that would be then the solution, what we have here would be the solution u of x0. That is, our u0 of x would be this solution here. What can we say then? We know then that each point, say this point here, that has the velocity 0, that will not move. So there is no movement. If we are at a point here, let's say, this would say be our x first, our x0 here, then we have at this point, we have this velocity here. So that would be the u0 of x0. So that would be then the slope of the characteristics at that point. So if we are then here having the x0, then we would have a characteristic line that has this value of the slope. So maybe this, so it would be the dx of t, dt would be the u0 of x0. So it would be simply constant. If we would go to another point, say that would be another point, well, let's call that x1, then we would have here in this example a higher velocity. Here the velocity was here, here the velocity is there, so it would be the u0 of x1. So if we go here, we have here the x1, then the slope would be here u0 of x1, which is higher. So that means we will have maybe something like that. So the slope here would be then u0 of x1. And if we want to know where the solution is, then after a certain time t, let's assume we want to see, let's see, if we are, say we take this time here, so we want to know what is happening at this time. Then we know the solution that was first at x0 will now be at this point here. So at this point here, this distance here is then the velocity that we have in this point, that is the u, well, enlarge that, that is the u0 of x0 times t. That will be then the distance that is then traveled in this interval. And that means the solution that we have here will then have traveled the distance here. So this distance, so the solution will be here. Let's see, I'll try to find another color here. So that would be then the solution. It would be here. So that would be the solution. It has traveled here. It has the same velocity. It has just traveled this distance u0 of x0 times t. At x1, the point that we have here, that has traveled with this velocity, so, and that has traveled then to this point here. So this point here, and this distance that it has traveled, this distance here will be the u0 of x1 times the time. So that means this has traveled with the same velocity, because the velocity is constant on the characteristic, up to here. So that will be then, let's see, that will be here. So it has the same velocity. So you see everything is shifted to the right, and the more, the higher the velocity is. So if we imagine that we combine it, and this will even be transported further, maybe we get something like that. So that would be then the solution u of xt. You see, the solution here is simply transported with its own velocity. Here, that is then transported. So this is transported here, and this is transported here. And if we are here, that will be transported here. So we get a simple transport, and you see, when we continue that, we will get here what from the sign, it will get more and more like a straight line. And if the sign goes down here, we can imagine that we can get a shock actually from that. The discontinuity will evolve. So that gives us then an idea what is happening and what we can use these characteristics for. We can go further and look for special cases. And these special cases are simpler than what we have here in the example, the part of the sine wave. We simply look at discontinuous initial conditions. And we look now at an initial value problem, at initial value problems for, that is for the implicit Burgers equation. Repeat it here. No, sorry, it is for, we do it here now general for a scalar 1D conservation law. But you can always have in mind f of u equals u squared half. With a piecewise constant initial condition. Piecewise constant initial condition. And that is the following, that is 9. We have u of x0. Here it was, the initial condition was some part of a sine wave. Now we take much simpler, we take constants, ul for x smaller than 0 and u right for x greater than 0. And this together, this initial value problem for the scalar conservation law with this piecewise constant initial condition, that is called a Riemann problem. So this is called a Riemann problem. So we have an initial condition that is constant to the left of 0 with ul and constant right with ur. And with that initial condition, we want to solve the 1D scalar conservation law. That is, the name is due to Bernhard Riemann, the mathematician who investigated such problems. Now we can look at two kinds of problems. The third kind is trivial. If we have u constant, ul equal to ur, we see then, we can imagine that then f of u x is then, if it's constant, it's 0 and ut is 0. So that is not interesting. The interesting thing is when ul is larger than ur, and that is one case, and the other case when ul is smaller than ur. So these two cases are interesting, and those are the ones that we shall look at, and for those cases we have in fact exact solutions that we can derive and that we know. So we shall look at these two examples. We'll do that next time, but I already give them here. And the result of the first one will be a shock when ul is larger than ur. And we will get, that will be the first example. And the second example that we shall study will be the so-called rarefaction wave that we will get for ul smaller than ur. So here we will have this situation here. X, here we have 0, and here we have the u, here we have the ul, and here we have the ur. And the shock, that means that we have a discontinuity that will propagate like that. So that, and this discontinuity, that is called then the shock. So that we have in this example, and the rarefaction wave, it's just the opposite. We have x and u, and we have this and this, for example. Then this will propagate with a lower velocity, and this will propagate with a higher velocity, and we will have something straight in between. So that is then called a rarefaction wave, and that is called a shock. So we'll look at that next week. The program for this week: tomorrow there is another guidance hour from 18 to 20 in R54, and on Friday is the deadline, and please note, Sondra Halden, the teaching assistant, would like to have your exercise 2 by 13:15, because there's 3 in the afternoon and you can start correcting your exercise 2. So on deadline on Friday, 13:15. And next week we start with a new feedback on exercise 2 and answers on questions on exercise 3 on Monday, 18 to 20 in the next lecture, then on Tuesday from 10 to 12.